Well, first of all, Sarah and Michael, thank you very much for organizing this conference. And I think it's a fantastic opportunity to build some community on vLamax research or simply glycolytic research, because we all had a big look at oxidative phosphorylation. But of course, there's another important major pathway of energy metabolism, and that's glycolysis. And however, because many of the key publications are in German, everyone sort of doesn't really know where's all this coming from. And because I've studied with Alois Mader and Hermann Heck, and I believe Hermann Heck is in the audience. So hi, Hermann. Great to see you. And you have been a fantastic teacher. So I'm trying now to sort of give some information about what I call the confusing history of the vLamax and why we propose a vLapeak. And actually, on the way to this, we've been working together with Anastasios Kabazakalis or Thanasis. And then also we got in contact with Stephen Seiler. So hi, Stephen, if you're here. And of course, Hermann Heck, who knew all the history of this. Okay, let's get started. So first, the good news is we've been working for a very long time on a manuscript to try to present this history. So where is the vLamax coming from? And actually, there are different versions of the vLamax, which confuses a lot of people. And so we recently got news from Sports Medicine that our review is the vLamax for glycolysis, what the VO2 max is for oxidative phosphorylation, has been accepted. So we are, of course, very happy with this. So let's start with a sort of an overture. It's a Cologne Sports Medicine group and Alois Mader's model of human energy metabolism, because if you get a little bit an idea of the background that led to the development of the vLamax. So this is a group. It definitely looks like 1970s if you just have a look at the hairdos. So the group was led by Wilder Heumann. Wilder Heumann is a fantastic physician. And he did sports medicine at the German Sports University of Cologne. Here's Hermann Heck, then Richard Rost, who unfortunately passed away quite early. And then here's Alois Mader, who really had the idea about the vLamax. And this was in 1979, this image. And it was a very active research group. And just also to highlight some of the things, what they did in Cologne. So Claude Bouchard recently wrote a paper about his sort of biography in Science. And in 1963 and 1965, he actually joined Wilder Heumann's group. And he considers Wilder Heumann as his mentor. And if you see, I mean, Claude Bouchard, after Benxoltin, for me, was a really, really, really big exercise physiologist. I mean, single-handedly, he completely did all the main research on sports and exercise genetics. And so he actually started his journey in Cologne under Wilder Heumann. Also, another thing, in 1963, Wilder Heumann published a book, so not a paper, in German, with the data of 2,834 VO2 max tests. So this is over 60 years ago. And this is of women and men aged 6 to 80 years. And if you ever need a figure that shows how does a VO2 max in the normal population change over time, well, get this book. I actually sent it to Mike Joyner, and he nearly fell off his chair. He thought this is just absolutely outstanding. And if you see the other things they've done, arterial blood sampling, development of lots of methods, and it's just absolutely sensational what they've done in these early days. In the 1970s, Alois Mader and Peter Hase in Halle in Eastern Germany, so they developed a method to measure lactate in microliters of earlobe blood instead of milliliters of arterial blood. So you have to imagine this is a big game changer for all of us, because in the early days, they needed to take arterial blood samples. And I'm sure you would be quite nervous taking an arterial blood sample because, I mean, it's a high pressure system of your circulation. And taking arterial blood sample is not very simple, but this is how they measured lactate. And then Alois Mader and Peter Hase, they realized, okay, we can take tiny samples from the earlobe, and this is arterialized blood, and we can measure lactate in it. And then Alois Mader, he went over in the back of a car to West Germany and then joined the group of Wilder-Heumann. So the key publication was in 1976. It was just after Kalman Wassermann described the ventilatory threshold. And then they introduced a paper in German that introduced the first lactate threshold. So this 4 millimole lactate, fixed lactate threshold idea that was in that paper. They also proposed a 3-zone training model. So below the lactate threshold, at the lactate threshold, or above the lactate threshold. And actually, I have to mention, they didn't call it lactate threshold, but aerobic anaerobic transition. And then they also realized that the power or speed at 4 millimoles of lactate is a better biomarker for endurance performance than the VO2 max or heart size. Yeah, and this really was very influential, this paper, because in Germany, then everyone shifted from VO2 max testing to lactate testing. Then in 1984, Alois Mader developed and first published in what is called a habilitation. It's another form of thesis before you become a professor, a super sophisticated mathematical model of human energy metabolism that simulates phenomena such as the slow component of the VO2. And also in there, Alois Mader first proposed the vLamax. So it's as old as 1984. That is probably the first publication where the vLamax has been mentioned. In 1985, Hermann Heck, he came up with the concept of the maximal lactate steady state. And in 1994, Alois Mader suggested a second version of the vLamax. And this was actually a vLamax test with a TR-lac correction. And so many of these things are not known in exercise physiology because many of the publications were in German, simply because the big three, so Alois Mader, Hermann Heck, and Wilder-Heumann, neither of them spoke English. And so I know Hermann, actually, he went to the gymnasium and he's very good in ancient Greek and Latin, but he didn't learn English at school. And of course, that affected the communication with the rest of the world, while people became, of course, very well known in Germany. So let's briefly, to understand the context of the vLamax, of the first mention, Alois Mader in 1984 came up with a sophisticated computer model. So he had a crazy idea. And the idea was that we put some input variables in. So for example, given the power during that you produce when you go cycling, then glycolytic power of the individual who does that exercise. And this is actually where the vLamax comes into play. Then oxidative power, the VO2 max, and then body weight and active muscle mass. And so he wanted to know, his idea was, can I now simulate what's happening in this black box that connects the input? So a certain metabolic person doing a certain type of exercise to the output, to the metabolic output. And the metabolic output is a concentration of ATP, ADP, AMP, phosphocreatine, inorganic phosphate, lactate, glycogen, glycolytic flux, and the lactate concentration, oxidative phosphorylation flux, oxygen uptake, and many more variables. And I think even today, this would be a crazy challenge to try to do that. And so the basic idea of this model is that Alois Mader was converting the workload and the other variables characterizing the metabolism of the exerciser to a rate of ATP hydrolysis, because the harder you exercise, the more ATP you break down. And then he used this then to calculate the concentration of phosphocreatine, ATP, ADP, and AMP. And he assumed that especially ADP and AMP were activators of glycolysis. So this is this equation here. And he also estimated that the pH, which is a hydrogen ion concentration, so shown here, that this was inhibiting glycolysis. And this is based on published data. It's a little bit simplified, though, because we know more regulators that activate phosphofructokinase, a key enzyme of glycolysis. And then he also came up with an equation that simulated oxidative phosphorylation, so your oxygen uptake at the exercise. And he assumed that ADP was a key activator. So if you want to see the whole model in all its glory, that's how it looked like. It is 33 equations. And I'm sure if people who ever had a look at this paper, they actually have this question. Alois Mader, and I would like to mention his 90th birthday is in 4 days on the 10th of June. So they thought, I mean, someone who comes up with 33 equations to try to simulate human energy metabolism and especially the response to exercise, either this all doesn't make sense and he's a complete madman, or he's an absolute genius. And I'm on this side. And actually, if you have a computer version of that model, it actually simulates a lot of phenomena of human exercise metabolism. So this is the overture. This is the background to the birth of the vLamax as a variable. So this is actually from his habilitation, but this is actually from the 2003 paper where he puts all these 33 equations in. And this is a direct screenshot. So the vLamax, V is for velocity and the rate of the reaction. And this is, he writes LA. So this is essentially, if you look at glycolysis as a reaction that produces lactate as the end product. And then this is a maximal rate. And so he needed that for his simulations because, for example, given also in the Michaelis-Menten kinetics, in all these equations where you try to simulate the rate of the reaction, you need the maximal rate. And for glycolysis, he defined the maximal rate of glycolysis for V, LA, max. The maximal rate of glycolysis expressed, and this is important now, as rate of lactic acid formation millimoles per second per kilogram. And this is, of course, not a kilogram of blood. This is a kilogram of muscle. So this first version of the vLamax, which appears here in this formula, and this is very similar to the Michaelis-Menten kinetic formula. This vLamax is a theoretical variable. I believe no one has ever measured it. I also believe it's virtually impossible to measure this, even if you take muscle biopsies. You can measure the rate of phosphofructokinase, but you can't measure this version of the vLamax. And the first publication is Alois Mader's habilitation. So it's another thesis in Germany, which he used to need to become a professor. I never had one because I was for 18 years in the UK. And this has been published in German. And of course, the international community is not aware, or many are not aware of this. And even if you're aware, it's very hard actually in Germany to get your hands on the habilitation of Alois Mader. So, but there's now a second variant of the vLamax, and we call it the vLamax blood. So we didn't just write B or so, because we wanted the nomenclature to be as intuitive as possible. So this is from our review that will come out hopefully in a couple of days or weeks. And this is a vLamax that can be measured. So the background to this is this book chapter here. So it's not even a publication where you could get it on the internet or so. It's a book chapter. And it's a book chapter from 10 years later in 1994. And this is a variable that people now measure. And so in this book chapter, Alois Mader had a look at the glycolytic tests at the time. And what people doing, they were running 400 meters, you get a very high lactate concentration. And then they said, the higher the lactate concentration, so the more glycolytic you were. The issue with this is that a 400-meter run also has a sizable contribution by oxidative phosphorylation. So it's not all primary. Glycolysis is really important, of course, for a 400-meter runner, but also oxidative phosphorylation. And so this is the original formula, vLamax. Yeah, here the V is enlarged, but normally to be consistent with also what people use in biochemistry, we propose a small v, just a normal v and no dot on top, making it as quite simple also to type it, but it is in italics. Yeah, so v, LA, and then we don't put a comma here, we just carry on vLamax and then blood to show what we mean. So this is a vLamax related to a liter of blood. So here's a typical formula. You would do an all-out exercise test, for example, given on a cycloergometer. You measure lactate before that test, and you measure lactate after that test. And you can have a look at the publication of Michael and Jamie. So they investigated that, and they had a look at all of this. And then the math is very simple. you take the maximum lactate concentration after this all-out bout of exercise minus the resting lactate concentration. And this is now not like the first variant of the vLamax related to muscle. This is related now to a liter of blood. And then you take the time of the exercise, which of course you define in your test, for example, given 10 seconds. And then in 1996, Alois Mader already realized that, of course, not all these 10 seconds you have maximal lactate synthesis. So it's a correction factor that you really try to estimate the true maximal rate of lactate synthesis or lactate accumulation. So in here, the correction factor, and you call it T-ALAC. And so this factor is usually 3 seconds for a 10-second test, or it is estimated individually as the time it takes for the mechanical power output to drop 3.5% from its peak, and that is Sebastian Weber. So Sebastian Weber is associated with Insight, and they've been doing, I believe they've been doing vLamax test with Jumbo-Visma and top triathletes and people like that. So to summarize here, this is the second version of the vLamax, again proposed by Alois Mader, and this is a testable vLamax that many people now test, and there's quite a bit of a discussion now about the T-ALAC. Yeah, what is the right way of doing it? How should you do this test? And so this is much discussed. Yeah. Now, actually, so thanks to Hermann Heck, he has simulated this, what you see here. So this is now sort of a simulation of the metabolic changes. And this is a simulation with Alois Mader's model of human energy metabolism, doing a constant load test. So that's, of course, a little bit different than a real vLamax test, because there, of course, you have an all-out effort, and then initially you produce more watts than later. But this load test causes phosphocreatine depletion after 11 seconds. Now, what happens during this test? During this test, of course, initially you break down phosphocreatine, yeah, and it takes some time for lactate synthesis. So that is vLA steady state. So don't worry about this, but this is essentially the rate of lactate synthesis. And what you see is you need a couple of seconds for lactate synthesis to kick in. Then it quickly increases. And if Alois Mader's equations are right, the key driver of this is a rise of the ADP concentration. So ADP increases then, and this is a key activator together with AMP of phosphofructokinase, the rate-limiting enzyme of glycolysis. But once you produce now lactate, associated with that is a drop of the pH. And there's really good literature demonstrating if the pH drops, that inhibits glycolysis. And there's, of course, now an issue, because if you really say you're measuring the vLamax, it occurs here, but is it really the maximum that you could achieve in a cuvette? The problem is that during such a test, ADP is increasing. So probably in vivo, during such a test, you don't get a maximal activation of phosphofructokinase. So glycolysis will not be maximally activated. So the true maximum that you can reach in a cuvette or an Eppendorf tube, yeah, if you add a maximum concentration of activator in, and if you keep the pH absolutely constant at 7.4, then you would get the true vLamax, so the true maximum rate of the reaction. So here in this situation, even though you do all-out exercise, the ADP still increases, suggesting that glycolysis is not maximally activated. And also once you start to produce lactate, then actually the pH starts to drop. And if the pH drops, the optimum is 7.4. So once it drops, also the rate of glycolysis is going down. So to be honest, in vivo, you probably never ever, no matter what exercise you do, the true maximum rate of glycolysis. So this behavior that the pH increases at the onset of exercise, I did my PhD on phosphorus NMR spectroscopy of human muscles. And this is a well-known phenomenon, might surprise some people. Normally, the intramuscular pH is 7. It increases initially because you start to build some inorganic phosphate, which is a super buffer. And that helps also to activate glycolysis. But once you produce more lactate, as here, once the rate of VLA, so the rate of lactate synthesis goes up, then you see the pH goes down. And this is actually what I was seeing in my human experiment when I put people in an NMR spectroscopy machine. So now, thanks also to Stephen Seiler. Stephen, if you're in the audience, good to see you. Well, good. I can't even hear you. I can't see you. I just assume you're there. So thanks a lot for being sort of the critical friend, as you told you, because you've heard about the vLamax, and so we came in contact discussing this, and you said, well, actually, I'm not so sure about this. So if you're interested, I could be involved in your manuscript and then actually ask critical questions. And I can always recommend something. If you have someone who's not sure about your ideas or even might be critical, take these people on board, because you really get better as a result of that, because you have to overcome the issues that this person names. And this was a fantastic collaboration with Stephen. So we actually identified then also, and thanks to the reviewers of our manuscript, initially we discovered 4 issues with the vLamax blood, but actually we believe there are 6 issues. So the first one I've already mentioned, doing an all-night exercise test, ADP is still rising, so it won't maximally activate phosphofructokinase and glycolysis, and the pH already drops, so it starts to inhibit phosphofructokinase and glycolysis. So the conclusion is you never, ever get the maximum rate that you could get in a test tube. So the true maximum rate of glycolysis, first problem. The second one is also lactate synthesis will only peak briefly. So it's not that it goes up and then stays up, but it only peaks briefly and then goes down a little bit. The second one, if you do a vLamax test, well, with a VO2 max test, you know you've reached the VO2 max because you get the leveling off. However, when you do a vLamax test, you're completely blind. You have no idea, even if it was possible, and I doubt it is possible to reach a true maximal rate of glycolysis. Even if it was possible to reach it, you have no idea you've reached it. Yes, you have no criterion to say we've reached the vLamax. There's no correction for lactate clearance. There's no correction for ATP resynthesis by oxidative phosphorylation. And the TR-LAC correction that Alois Mada has introduced is based on very little data. So people sometimes argue, oh, how should we correct for the TR-LAC? And because Alois Mada have proposed it, so they think, should we use a power drop? Should we subtract 3 seconds, 4 seconds? But all of this is based on very little data. And we thought, well, is it actually worth measuring the vLamax? And we said, hey, guys, why don't we keep it simple? I mean, like with the VO2 max, if you're not sure you've measured the VO2 max, you call it VO2 peak. And why don't we do the same with this test variable? Why don't we just measure a vLapeak, which is a peak rate of lactate synthesis per second that you can measure in a well-defined test of 10 to 15 seconds. To us, this is the honest way. First of all, you're honest because you don't claim you've reached the VO2 max, but you're just reporting the peak rate in your test. And it's a very simple way, because we propose also, let's avoid all this trouble we have with the TR-LAC, because we just remove it. So a vLapeak would be just, according to the definition we propose, it's a 10 to 15 second duration test all out. Any mode is possible. You just have to report this very well. Make sure you are not glycogen depleted. Measure lactate at rest. Subtract it from the maximal lactate concentration after exercise, and then divide it by the time of the exercise. And what you will get is the peak lactate accumulation during such a test per second. And I feel this works much better, and this solves a lot of problems where we counted 6, and maybe there are even more problems with the idea of measuring a vLamax. So this is what we propose, what we should do. And now, towards the end of my talk, I believe I have 10 more minutes. I would like to just show some of the implications. So why should we actually measure the vLamax or vLapeak? What does it mean for our metabolism and for performance? And I'm super grateful to Hermann Heck. Hermann Heck, I call him the oracle of Cologne, the lactate oracle of Cologne. Whenever I have a question about lactate, I just phone Hermann, and I usually, in 99.9%, get an answer. Alternatively, I get an idea, a really good idea about an experiment that one could do. So let's have a look. So this is key data here. And this is simulated again with Alois Mader's model of human energy metabolism. And this is Hermann Heck. He is actually probably more research active than many PhD students, because we also work on another manuscript with Hermann. So he is, of course, a fantastic mentor and teacher. And so I'm very grateful for him for all of this. But so what has he simulated here? So here we assume three persons. Everything else is the same apart from the vLamax. And in this case, because it's a model, it's a vLamax muscle. So it's related per kilogram per second. So it's not per liter of blood. It's a different variable than you measure in your vLamax blood test. Yeah, so don't confuse the two. There should be a conversion between the two. That should be possible. But this is now the vLamax version that you need to feed the model of Alois Mader. And here we have three people. So their VO2 max, their oxidative phosphorylation, their body weight, all of this is the same. But the normal person has a vLamax of 1 millimole per kilogram per second. The more glycolytic one has one of 2. And the least glycolytic one, the slow twitcher like myself, has a vLamax of 0.5. So that's a typical graded exercise test, one thing which has really been developed to perfections by the people in Cologne. And so here you see every 3 minutes, you increase the workload by 50 watts, and then you get the typical lactate curve. And this is now simulated, not experimental data. So here's a normal person. So many of you probably think that the ultimate endurance athlete is an athlete with a very high VO2 max or oxidative phosphorylation capacity, many mitochondria, but on top of that, loads of glycolysis. But let's try to simulate that. Let's increase glycolysis from a vLamax of 1 to 2. And what you see is now, surprisingly, maybe to some people, you get a leftward shift of the curve. So that indicates endurance performance in a time trial would actually go down. So why is that? Well, it is because a higher vLamax, if everything else is the same, means more lactate synthesis. So it's more lactate running into the bathtub. There might be the same rate of oxidation and clearance of lactate, but as a result of that, at every exercise intensity, the lactate concentration is higher than in a person with the same oxidative phosphorylation, and VO2 max, but where the vLamax is lower. And now you say, okay, I have a Tour de France sprinter. Now, in order to win all these sprints and attacks, he needs to become, or she needs to become more glycolytic. So then it goes and left. Sorry, I confused myself. But now if you reduce the vLamax, then actually you get a rightward shift of the lactate curve, which you see here. Yeah, because the reason for this is at every exercise intensity, because the vLamax directly affects lactate synthesis, you have less lactate synthesis if everything else is the same. As a result, you have a lower lactate concentration. So is there any evidence for that? No direct evidence, because it's very hard to manipulate the vLamax. Yeah, you can't just take phosphofructokinase out of a living human muscle. But actually, one thing that is comparable to a drop in the vLamax is actually glycogen depletion. So we know well from Eric Richter and others' work, if you reduce glycogen, then actually the rate of glycolysis is going down, which is comparable actually to having less glycolytic enzyme. And this is data actually by the team of George Brooks already in 1982. So here is a work rate. So you could convert that into power, typical lactate graded exercise test. And the green curve, that's the normal curve. And now you do glycogen depletion, which is comparable to a drop of the vLamax, and you get that rightward shift. And if you go back to here, so here in the simulation, here you directly lower the vLamax, but also if Hermann now in this model would lower glycogen, which is comparable to a drop in the vLamax, you again would get this rightward shift. And also the peak lactate in such a test is predicted to be lower. So actually, sort of there's some indirect experimental evidence already from 1982 that something which works similar to a drop in the vLamax has a similar effect like the simulated effect in the vLamax. So going back to this one, now this is of course quite important now also for working with your athletes. So if you have an athlete with a given amount of oxidative phosphorylation or given VO2 max, now you have to see what type of sport am I in. Are you doing like a triathlon, Ironman triathlon, where you don't want to sprint, you want to really maintain a constant exercise intensity from start to finish. So you want to make your athlete as little glycolytic as possible. You really want to lower the vLamax, because then you get the rightward shift of the lactate curve. And then if you have to exercise, say, with 250 watts, the lactate concentration is lower than if you had a more vLamax. However, now, if you now have a Nordic skier where you really have to sprint up the mountains and you slide down the mountains, and for going up the hills, you really need more glycolytic power, then actually you now have to sacrifice some of your aerobic endurance. So you have to really sacrifice your lactate curve shifted to the left for being more glycolytic, for being better on the uphill beds. And that applies to all sports where you need some sort of glycolytic component. Also games like football, if you need some glycolytic power in there, you don't want to bring the vLamax as low as possible, but you now need to compromise. And you need to find the optimum between your oxidative capacity and VO2 max and your glycolytic power, which is expressed by the vLamax. So, and then Hermann also had a really cool case study. So we had some very good German rowers. This is one of them. And actually rowing is a sport, so where you row over 2,000 meters. And this is a mix between glycolytic power and oxidative power. So these guys, we had 3 rowers, A, B, and C, and they did a 2,000 meter test. And sort of the power was nearly 500 watts. And then if you looked at the power at 4 millimoles of lactate, it was hugely different. This guy had a power at 295 watts at 4 millimoles of lactate. This one at 372, and this in between. And if you just look at sort of a standard lactate test, then you would say this guy is not fit enough and this guy is really good. But then they measured also, this is true experimental data in this rower, the vLamax doing a slightly longer 20-second rowing test. And so you see this guy is more glycolytic. You also see peak lactate is 22 millimoles. This one here is medium glycolytic, and this one is least glycolytic. And so actually, this guy A, the rower A, achieves this performance by being very glycolytic, but less oxidative. This rower is good in both. And this rower is highly oxidative and achieves this high performance mainly via his oxidative phosphorylation, but less via glycolysis. So different ways lead to Rome in rowing. And so this really also shows that if you don't measure the vLamax in these people and just do a standard graded exercise test with lactate measurement, you don't get the wrong picture. As Hermann Heck always says, if you don't measure the vLamax, you're blind on one eye. So measure the vLamax, because then you also get an idea about your athlete's glycolytic capacity and not only about oxidative phosphorylation. So just to summarize now and finish my talk, the vLamax muscle is the first variable. It's Alois Mader's habilitation, 1984 in German. The vLamax blood is the second version, completely different numbers, even for the same person, than the vLamax muscle. And it's a 1994 book chapter in German. However, there are some problems associated with this, one being that you probably never reach a maximal rate of lactate synthesis in vivo, the true rate, and this is why we propose a vLapeak. We aim for a simple and self-explanatory nomenclature, so you might want to adopt this. So just a V in italics, vLamax, and then muscle and blood, and please spell it out. I think in exercise physiology, there are often too many abbreviations that makes everyone confused and make reading the papers a pain. If you spell out this is muscle, if you spell out this is blood, then everyone knows what you mean. There's lots of research questions. We need to validate vLapeak test or vLamax test, maybe with biopsies, measuring muscle phosphorufructokinase activity. Do the two correlate well? We need to develop and optimize tests for different sports and maybe even for specialist populations, maybe for the elderly, maybe for people with diabetes, yeah, because glycolysis is a key pathway of getting rid of glucose. How can we convert the vLamax into vLamax muscle? And the implications, can we verify these predictions experimentally? And then also, I think really it's also important for the health implications, yeah? When we age, our glycolytic power decreases, but we never measure that. Can we develop a vLamax peak for the elderly? And also glycolysis utilizes blood glucose, so this might be relevant for the diabetics. So finally, I'm sorry, running over time. I agree with Michael, we should have a happy, friendly field. That should be our aim. And let us become a supportive research field where we support each other in our goal to measure the vLamax peak and to determine its importance for human performance, metabolism, and health. I thank my team, Tanase, Stephen, Hermann, and of course, Michael, for you for supervising. This is our support. And I end with a picture of Demi Wollering overtaking me twice on Christmas Eve 24. Thank you very much for your attention. And sorry for being a little bit over time.
Excellent. Thank you very much for that, Henning. That was really insightful. So if anybody's got any questions, please do pop them in the chat now. I think I've got one question to start off with then. So you mentioned about the conversion between vLamax muscle and blood. Do you have any idea of what that conversion might look like?
Yeah, I think a way of doing it, you really need the model of Alois Mader, and Hermann has the computer version of it. And then you can simply do a vLamax test, put all the other variables of an athlete into the model some exercise, and play around with the vLamax muscle until you get the data that you see in the experiment with your athlete. And I think that would be a way of getting a conversion.
So we've got a couple in the chat now. So Oliver Quickman mentions, so he's talking about you want to be as little glycolytic as possible in triathlon. Did you refer to long distance events since short distance triathlons, especially on the bike, demonstrate rather high power profiles? Or would you agree that some glycolytic types can be successful over both distances?
So for long distance, for sure, you want your lactate curve as far right as possible. And you have two ways of doing it. One's becoming more oxidative, getting more mitochondria in your legs. And the second one is lowering your vLamax, yeah, because then less lactate is running into your muscle. For short distance, it's a really good question. I think I would ask Hermann to do the simulation. Because that's the beauty of the simulation. Once you've played around with it, you realize that this actually simulates phenomena quite well. And then you can put the power during the cycle right in there, and you can play around with the vLamax. And you have to say, how much glycolysis do I need? How much vLamax do I need in order to perform best in that event? So I couldn't answer it just now. I would just guess. But I think with the simulations, you could also address that problem.
So last question for myself then. So you kind of alluded to this towards the end. So do you think it's actually possible to validate the vLamax, and how might we go about doing that in the future?
Yeah, I mean, you couldn't directly, we had quite a discussion with our reviewer, how you could validate it and whether you could actually measure the rate of lactate accumulation of a muscle biopsy. I know Sebastian Weber, he will also, Sebastian Gehlert will give a talk today. He does muscle biopsy studies. Hi, Sebastian. You're really important for German sports science because otherwise hardly anyone does it. And so you could, of course, do now vLapeak tests. This is what we suggest because simply we don't believe that you ever reach a maximal rate. And like with a VO2 peak, hey, be honest, say, we are not sure we reach a maximum rate. Let's call the baby VO2 peak. And no one can criticize you because you're not claiming you reach a maximum. And so you do these tests, you take a muscle biopsy of the vastus lateralis, you do a phosphofructokinase assay because you're pretty close to it. And then you could simply see the hypothesis would be that those people with a higher vLapeak, that they would also have a higher rate of phosphofructokinase activity in their vastus lateralis. It's a relatively straightforward experiment, and people like Sebastian Gehlert, they have the opportunity to do such tests, and we just need some funding for that. And maybe we can collaborate with a lot of people, yeah, in order to try to get this validation experiment done and publish it maybe in Journal of Physiology.
Yeah, I agree. I think that's the next step going forward, isn't it? Is if we can validate it, then everybody can feel a bit happier about using it. Yeah, excellent. Well, thank you very much for your talk.